In this video, I'll be talking about dynamic range in images and how image noise affects that. There are multiple steps in the imaging process, and each one of them can add noise to the data. Light from a light source is hitting the object. This light could add noise. It could be flickering, it could be non-uniform, or have a distinct color cast. The light then passes through the lens, and the lens can add geometric or radiometric distortion. The light is projected onto the image sensor and turned into an electrical signal, adding additional types of noise. Reading the electrical signals out of the pixels and amplifying them will add some noise from the electronics. And then additional quantization noise is created as the signal is being sampled at, for example, 8, 12, 14 or 16 bits. The image data can be packaged into a raw file containing the unmodified sensor data, or it can be processed further into a TIFF or JPEG with some additional loss of data integrity. When using an image sensor to capture and digitize an image, 4 distinct types of noise are generated: photon shot noise, readout noise, fixed pattern noise, and quantization noise. Photon shot noise arises from the fundamental randomness of light and of counting photons. Imagine an image sensor as an array of small teacups placed outside in the rain, and the raindrops as the photons of the light. To control the exposure of our rain sensor, we remove a lid from all the teacups, then let the rain fall into the cups for a set amount of time, and then close the lid again. We now count the number of raindrops in each individual teacup, thus creating our digital image. If we just remove the lid and count raindrops for a very short time, so that on average maybe 1 drop hit each teacup, we will have 1 in this one, 0 in that one, 2, 2, 1, 0, maybe 3 in one of them. This image signal will be extremely noisy. If we then instead count a little bit longer, so on average we have 10 raindrops in each cup, we will maybe have 6, 8, 11, 12, 9. Already there it starts to kind of average out and become less noisy. Then we count to 100. We will have an even more smooth signal of maybe 94, 108, 102, 87. So the more raindrops we count, the more even the level in each cup will look. We can see from this example that as we count more and more raindrops, the absolute difference, the random difference between the cups actually do increase, but the base level of the amount of water in the cups increases more. So the ratio between the signal, the level of the water, and the noise improves significantly. Image sensors, of course, do not count raindrops but photons, but the principle is exactly the same. Each pixel has a photosensitive area, the pixel well, that when hit by a photon, an electron is released and captured in that well. And during the exposure, that well slowly fills up with more and more and more electrons, and after the exposure, these electrons can be read out of the pixel well and turned into a digital signal. When looking at this mathematically, we see that when counting something random like photons or electrons, the average noise is the square root of the count. So even though as we count more and more and more, the absolute noise will increase, the good signal increases much faster. So the more we count, the better the signal to noise ratio will be. So in imaging terms, this means that it's important to capture as much light as possible and fill the pixels with as many electrons as possible to get the best possible signal to noise ratio. If we underexpose, we end up capturing fewer photons and collecting fewer electrons in the pixels, thus having a worse signal to noise ratio. And if we then amplify this signal to compensate for the underexposure, we just amplify all that noise up. On the other hand, if we overexpose and fill up the pixel well above capacity, the data is clipped and we end up with unusable image data. To sum this up, to get the best possible image quality, we want to fill as many of the pixels as possible with as many electrons as possible without any of them overflowing and clipping. The electronics involved in reading the electrons out of the pixel wells, converting and amplifying them into a signal that can be digitized, will add a little bit of noise. This is what is called readout noise. In modern high-quality CMOS sensors, the amount of readout noise is extremely low. So the readout noise only becomes significant in the very, very darkest areas of the images, where the pixels have captured maybe about 10 electrons per pixel. Fixed pattern noise comes from small production differences between individual pixels or columns of pixels. But as the effect is the same from image to image to image, it can be very precisely handled by calibration and typically do not have any negative effect on the final image quality. When turning the analog signal from the pixels into digital numbers, it's important to use enough bits to faithfully represent the data. If too low a bit depth is used, it can result in significant quantization noise and banding. The dynamic range of a scene is the ratio between the brightest areas and the darkest areas. In real-life situations, this can be a very significant difference between, for example, a bright, shiny roof in direct sunlight and the deep shadows between the buildings. Or it could be a reflection from a white part of a wind turbine and then some details like within cracks between the elements. To faithfully reproduce such a scene, a camera that exposed for the brightest highlights to avoid any clipping must still be able to collect enough light in the shadows to reproduce detail even in the darkest areas. The dynamic range of an image sensor is mainly defined by two parameters: the ability of the pixels to count many photons in the brightest areas, and the level of readout noise, setting a lower threshold for how little light can be collected in the darkest areas before noise completely takes over. Readout noise of modern high-quality image sensors is already extremely low, so the main driver for higher dynamic range is the capacity for the pixels to count more photons. This is called full well capacity, and it's mainly limited by the physical size of the pixels. So when creating ultra-high resolution image sensors, it's important that the sensor chip is big enough to allow for large pixels that can collect high-quality image data with a high dynamic range.